section I'm going to talk about half-life. This can kind of be very confusing for some students. We're going to use this to calculate radiometric ages in the lab. So I'm going to walk you through how to do this and what the half-life is. So the half-life is the time it takes for half the parent isotope to decay to daughter. So time it takes for half the parent isotope to decay to daughter. If you don't know what parent and daughter are, you should go back and watch the previous lecture on absolute age dating, because it talks about what those terms mean. This is a fixed interval of time for each isotope. What that means is each isotope has a set number of years it takes to undergo one half-life. So for carbon-14, it's 5,730 years. It will always be 5,730 years. It will never change. Temperature, pressure, time does not affect the half-life. It is constant. That's what fixed interval means. It is constant. So with each half-life, the number of radioactive parent isotopes is reduced by half. And since we can't destroy matter, the number of daughter isotopes increases by the same quantity. So total number of isotopes, total number of atoms present in the rock is constant. We can't destroy matter. Therefore, if we start off with 100 parent isotopes, after one half-life, it's going to decrease down to 50, and we're going to end up with 50 daughter isotopes. So we can write this out to show an example. So if we start with 100 carbon 14 atoms, so this is carbon 14. If you don't remember that's carbon 14, you should write that out. At time 0. So this means the beginning, or the start. So after one half-life, which took 5,730 years, YRS stands for years, we would have 100 divided by 2, because the half-life is the time it takes for half the parent isotope to convert to daughter. So it's 100 divided by 2 equals 50 carbon-14 atoms. Well, the other 50 don't get destroyed. The other 50 go to 50 nitrogen-14. So this is the parent, and this is the daughter. So if you add them all up, we still have 100 atoms. So after 2 half-lives, so this would be a total of 11,460 years, because it would be basically adding another 5,730 years. We start with 50 carbon-14. We divide that by 2, and we are now down to 25 14 carbon and 75 nitrogen-14. So basically 50 divided by 2 is 25, so we subtract 25 from here, add 25 to here, and we get that. And we get that. And if you add them both together, you still have 100 atoms. We can't destroy matter, at least not yet. So after 2 half-lives, this amount of time has passed. Geologists use radioactive decay of the parent isotope to daughter in order to determine age of rocks. So I'm going to show you how they do this. Okay. So T0 is the beginning or the start, so that's what it's going to look like. T0 is how I'm going to write it. You start with 100 parent isotopes and 0 daughter. If you have any daughter, this won't work. You'll get a wrong age. So in geology in real life, not all minerals are suitable to do this because they're not closed systems. So P stands for parent, D stands for daughter. So you can look at this as 100 atoms, 100%, but we start with 100 parent atoms, 0 daughter. After 1 half-life, T equals 1, so this is 1 half-life, if you're not going to remember that. We take 100 divided by 2 equals 50 parent and 50 daughter. Because remember, we have 100 here, and so we subtract from the parent, add to the daughter. After 2 half-lives, T2, we started with 50 parent divided by 2, because the half-life time it takes to convert half the parent isotope to daughter, equals 25 parent, because we subtract 25, add 25, 75 daughter. T equals 3, so this is 3 half-lives. 25 divided by 2 equals 12.5 parent and 87.5 daughter. You can keep doing this, going down, 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 until you want to, or until you get the half-life you need. So basically, it's the portion of daughter to parent isotopes that you're looking for. So in general, the questions would be like, if you have 25% parent isotope remaining and a half-life of 100 years, what is the age of the rock? So in a question, they're going to give you some information. They're either going to give you the percent of parent isotope or the number of parent isotopes, or the number of daughter isotopes or the percent of daughter isotopes. And they're going to give you the half-life. This is something that you never have to calculate. They're going to always give that to you because those are known. Those were done in the lab. They've figured them out. So the formula is age equals number of half-lives times the half-life. Oops. So we know the half-life, that's already given to us. We have to figure out the number of half-lives. Hopefully you're thinking to yourself, oh, well, we just did that. So that's basically what you do. We have 25%. So I would start with T0 equals 100 parent. I'm not concerned with daughter here because it doesn't say anything about daughter. So T1, after 1 half-life, I have 50 parent. Time 2, I have 25 parent. Oh, look, I have 25% remaining. I had 2 half-lives pass. So I would put 2 here times the 100 years equals 200 years. So our rock is 200 years old. Obviously, we don't usually deal with hundreds of years, we're dealing with millions and billions of years. But this was just a simple way to show you how this works. So it's based on the information. They can say percent. If they say percent, you just start with 100% and you divide. And so usually they're going to give you a nice round number to do this. You will have to know this formula for the test and for the lab. I will not give you this formula. Once you have the number of half-lives, you stop dividing and you're always going to be multiplying. A lot of students want to divide these numbers, but you don't. You're multiplying at this point. And the reality is, this is like an oversimplification of the process, and it's actually much more complicated, but it still gets the point across. Another important thing is you want to use the correct isotope for your sample. There are many isotopes that you can use, but they all have different half-lives, so different isotopes have different half-lives. So you want to use one that's close to what you need. At least 1 or 2 half-lives have passed, so you have enough daughter to actually detect anything. Another thing is you cannot date sedimentary rocks. Sedimentary rocks do not have the correct minerals present. If they do, you get an age younger than the sedimentary, you get an age older than the sedimentary rock. The reason being, certain types of sedimentary rocks are made from weathered and eroded other rocks. Well, you get the age of that original parent rock. So that doesn't help you. Usually date igneous and metamorphic rocks. With the metamorphic rocks, you get the age of metamorphism because it resets the clock. You don't get the age of the parent rock, you get the age when that rock was metamorphosed. We can date fossils only back to about 100,000 years, primarily because we're using carbon-14 and we cannot detect carbon-14 below that level. As technology gets better, we will be able to do that. Therefore, cannot date dinosaurs. Dinosaurs were during the Mesozoic. You're talking several 100 million years, not 100,000 years. So this is for very recent fossils. And they have to have the carbon-14. Carbon-14 sometimes gets weathered and eroded due to diagenesis. So during the fossilization process, so you don't get any carbon anyway and you can't date them anyway. So if we look at this table, this shows you your parent isotopes, your daughter isotopes, the half-life presence. So if you have a rock that is 800 million years old, you're not going to want to use 4.5 or the 14 billion. So it gives you kind of a range of when the dates are useful. And then it also tells you the mineralogy. These are igneous and metamorphic rock mineralogies. You can find some of these in sedimentary rocks, but like I said, when you do this, you're dating the original igneous rock that it formed in, not the sedimentary rock when that formed. And then your carbon-14 you can use to date anything that has carbon in it up to about 100,000 years. So you have to be very picky and choosy because this is also very expensive still to do. So you kind of have to have an idea of the age of the sample that you're working with.